A critical system experienced intermittent failures, manifesting as stalled transactions and delayed responses. Traditional monitoring dashboards, however, displayed all services as green, reporting normal CPU utilization and memory consumption. No alerts fired, yet the customer impact was undeniable. The engineering team faced a paradox, a system clearly malfunctioning, but offering no discernible evidence of its internal struggle. This scenario is common in distributed architectures. Services interact in complex ways, and a failure in one component can cascade or manifest indirectly, making root cause analysis exceptionally difficult with only aggregated health checks. The challenge lies in gaining true insight into the actual execution path and states within an opaque system. The solution is observability, not merely monitoring. Monitoring tells you if a system is working. Observability allows you to understand it is or isn't working, enabling you to ask arbitrary questions about its internal state based on external data. It shifts the paradigm from knowing the symptoms to understanding the underlying disease. Observability relies on three fundamental data signals: metrics, logs, and traces. Each signal provides a distinct perspective on system behavior, and their synergistic application is crucial for comprehensive understanding. Relying on only one or two offers an incomplete and potentially misleading view. Metrics are numerical measurements collected over time, representing a specific aspect of a system. Examples include request rates, error counts, latency percentiles, and resource utilization. They are aggregated and often time series data, ideal for dashboards, alerting, and identifying trends or anomalies over periods. However, metrics provide a high-level statistical overview. While they indicate is happening, a spike in error rates or increased latency, they rarely explain. A sudden drop in throughput might signal a problem, but metrics alone cannot pinpoint the exact failing request or the service responsible for the bottleneck. Logs are discrete, immutable records of events that occur within a system at specific points in time. They capture contextual details about operations, such as user IDs, request parameters, error messages, and stack traces. Logs are invaluable for detailed debugging and understanding individual component behavior. The challenge with logs escalates with system scale. High volumes of unstructured log data become difficult to store, parse, search, and correlate across multiple services. Without proper indexing and a robust aggregation strategy, logs can become an unmanageable ocean of information. Tracing captures the end-to-end journey of a single request or transaction as it propagates through multiple services in a distributed system. Each operation within the request path generates a span, linked by a unique trace ID. Traces visually represent the causal relationships and timing of operations. Distributed tracing reveals latency bottlenecks, identifies critical paths, and visualizes service dependencies that are otherwise obscured. It allows engineers to follow a request from its entry point to its completion, across numerous microservices, providing a precise timeline of execution and potential failure points. The true power emerges when these three pillars converge. Metrics alert an operator to an anomaly. Tracing helps pinpoint the specific service or operation responsible for the deviation. Logs then provide granular context and error messages within that problematic service, detailing the precise nature of the failure. Designing for observability begins at the architectural phase. It requires embedding instrumentation code into services from inception, rather than attempting to retrofit it later. This involves strategic placement of metric collectors, structured log generation, and consistent trace context propagation across service boundaries. This proactive integration transforms troubleshooting. Instead of reactive guesswork, engineers gain the ability to rapidly diagnose and resolve issues by leveraging a data-driven approach. Mean time to resolution, or MTR, significantly decreases as the path to root cause becomes clearer and more direct. Operational excellence is a direct outcome of robust observability. Continuous monitoring of system health and performance allows for proactive optimization, identifying resource inefficiencies, detecting performance regressions before they impact users, and informing capacity planning decisions with empirical data. Implementing comprehensive observability presents challenges. The sheer volume of data generated by large-scale systems requires significant storage, processing, and analytical capabilities. Managing costs associated with data ingress, retention, and querying across different signal types is a constant consideration. Selecting appropriate tooling for collecting, storing, processing, and visualizing metrics, logs, and traces is critical. Moreover, establishing standardized data formats and consistent instrumentation practices across development teams is essential to avoid data fragmentation and ensure unified insights. Observability fosters a crucial feedback loop for system designers. Insights gained from production data directly inform future architectural decisions, refactoring efforts, and feature development. It promotes a continuous improvement cycle, ensuring designs evolve based on real-world operational behavior. Ultimately, embedding observability into system design transforms complex, opaque architectures into transparent, understandable entities. It equips engineering teams with the necessary insights to build resilient, high-performing systems that can adapt and evolve effectively under demanding operational conditions.